Thank you for having me today. So I'm Alessandro Ossola. I'm a research coordinator at Macquarie University, but also assistant professor at University of California, Davis. So today I just want to talk briefly about our new global urban tree inventory, or friendly called GUTI. So this data set actually has a relatively long history. Is being collected through a project that we have here in Australia, funded by Oat Innovation, which is an umbrella organization that joins all the plant producers across the country. 5 years ago, we've been giving about $10 million Australian dollars to model pretty much the entire horticultural flora for its resilience towards climate change. So that original need essentially trigger the collection of this data set that has been used together with other available data sets of plant occurrences across the globe, for example, GBIF or the Atlas of Living Australia and others, to be able to essentially model niches, climatic niches of these horticultural species, and trying to predict which one of these species might be able to be suitable, for horticultural production and planting in 3 different climate change scenarios from 2030 to 2070 using the new CHALSA climatic data sets from the UK. So the need to essentially trying to understand to what extent plants can survive into urban environments, which is our target ecosystem, trigger this effort to try to collect as much data as we could in terms of occurrences of urban trees globally, to try to better estimate to what extent the realized niche in urban areas differ from the native niche in natural environments. So we started this, and it was quite painful to essentially source all these data sets. And I need to thank, all the team and research assistants and stuff that did a great job. Painful in the way that, as you can see, the collection has been divided in 2 main streams. One related to real tree inventories, mostly accessible through open data sets that are published by city councils or regional governments. These are all street trees, so that's potentially a bias, but it gives us an indication of whether a particular species might be able to live in a particular climate, and in a way gives us a semi-standardized way to understand that potentially the management that people do on these street trees might be similar in different countries, even though we don't have a definite proof about it. As you can see, most of the inventories are coming from developed countries where there is more, I guess, economic availability to go out in the field and count every single tree and measure them and so on. So we have a lot of data from North America, Europe, and of course, Australia. For other countries, we wanted to increase the coverage as much as we could. And so we relied on 3 species list published in gray literature and other, in the scientific literature as well. As you can see here, we managed to collect data for about 473 cities and towns globally. But this data collection was slightly different. So we tried to collect as much as we could, but since we were feeding most of this data in these species distribution models, and we are using Maxent as a tool to model climatically suitable habitat for these species, actually we decided to stratify this collection by climate orders, climate groups, in this case, Köppen groups. And as you can see, the number of urban areas in GUTIs in different Köppen groups are essentially kind of balance based on the amount of global area that is contained within each of these climate Köppen groups, as you can see here. So this was a way for us to reduce a bit of the sampling bias that was feeding into the different models. So we ended up collecting data in about 73 countries. We covered most of the Köppen zones, so 21 out of 29, and we covered about 19 ecofloristic zones from FAO, defined from FAO. So what we found is that if you look at the top graph, we actually recorded a quite astonishing number of species, 4,734 species. That gives us actually a relatively good sample coverage. However, if we extrapolate the likely number of species that might be present overall in urban areas, we estimate that this number might be pretty much twice as much, so more than 8,000 species that could be living in cities. These are all tree species, and pardon my difficulty in defining differences between shrubs and trees for some of these species, because it depends where they grow. So some of these trees might actually be shrubs in some areas and vice versa. But anyway, you get the gist that actually urban areas globally might be hosting a significant species richness of trees. In checking taxonomy, actually, we apply a double taxonomic check using both taxon stand and taxize in R, just to make sure that all the data cleaning pipeline was as strong as we could. We collected about 13 million original raw records out of all these different tree inventories and lists. And we firstly manually cleaned about 35,000 different entries of names that people assigned to each of these records. In some cases, in some little cases, we were able to recover the common name and assign a proper scientific name and a binomial to some of these points. But in some other cases, we couldn't, so we had to drop like instances where common names were assigned. Also, another caveat of this is that in this case, since we are doing bioclimatic models on a species level, we did not consider varieties, cultivars, cultigens, and so on in this particular instance, but it's something that we should be really doing in the future. So if we look at GUTI in relation to the known tree flora in nature that contains about 60,000 trees, we estimate that the diversity of trees in these urban areas might be up to 8% of all the non-tree species, which is quite significant in my opinion. So we have about 68% of plant families that contain trees and 29% of genera that are represented in urban areas. But if we look at the distribution within families, you can see here that actually about 1/3 of species belongs to essentially 4 different families that in a way species rich, of course, that's why there is this bias, but it's interesting to see that historically, I guess we, as humanity, we planted plants that were coming from particular families or genera overall. It's also important to say that most of the species that we found are actually singletons or doubletons, so they are only recorded in 1 or 2 urban areas. So species rarity across the data set is a fairly common trait. So you're more than welcome to download this data set. It's open access and freely available. We haven't started looking at invasion ecology using this particular data set, but essentially what we did, and I'm going to show you in a few slides, was to add to each of these species the invasiveness or the invasion status in each of the countries for which we have data from the Greece data set. Our main scopus wasn't invasion ecology here, is a slightly different thing. It's something that we hope to do in the future, but the data set overall is freely available, and essentially it contains all the taxonomy that we believe is correct to today, and there is a present absence matrix of the species times the different urban areas globally, plus additional information about the conservation status for some of these species as well. So how we've been using this data set. So this is just an example of how we apply this type of data. In this case, I'm just presenting a couple of Australian trees, Alocagerina tolorosa and Alocagerina verticillata. As you can see here, we can actually measure and quantify the different climate niches of the different species. As you can see on the left-hand side, the species as an urban niche overall, both for mean annual precipitation and temperature, that is slightly different compared to the native or natural distribution, I would say. Whereas for Alocagerina verticillata, you can see that the urban distribution and the urban niche completely matches the natural niche. Another thing, and here I need to credit one of my PhD students, that we're trying to do is trying to understand to what extent in the inclusion of records, urban records from GUTI, is essentially changing the climate niche of these different species. So this is an example from Quercus dentata. I need to thank Ronnie for providing, my PhD student Ronnie, for providing this slide. But as you can see here, Ronnie is trying to now model in a hypervolumetric space how urban records are expanding essentially the niche of different species based on a number of different factors that is accounting for example, like origin, the type of trees, and many other factors. From this 3D animation, you can see that the native niche here compared to the urban niche for these three different climatic variables is quite significant, and the overlap is actually quite minor. So what we found so far is that temperature is actually the main driver driving essentially two different distinct niches, urban and native niches. Precipitation is, of course, the second one. So this is not really something unexpected, I guess. It's something that we were expecting. Now we are doing this for several hundred species and trying to see whether there are commonalities based on the type of traits that these species have. This is another example where we use actually data from this paper where we essentially model the impact of climate change on 176 native trees to Australia. And in this case, we use that data to model how the average leaf length of the community in each of these significant urban areas across Australia look like. And as you can see here, at a community level, if we live, let's say, in Melbourne, so where the mean annual temperature is lower, your native trees have overall a smaller leaf size compared to situations where you live in, for example, in Brisbane, where the mean annual temperature is definitely hotter. So we can use this data set to, I guess, address several questions that are related to climatic niches from one side, but also on plant traits from the other side. Another application that we believe is important actually relates to conservation biology overall. Out of 4,700 species, we found that 6 species are actually technically extinct in the wild for IUCN. So these are the species that somehow we managed to conserve and preserve within the horticultural industry, and we are still, we can still find these plants commonly planted in many cities worldwide, but they are technically extinct in nature. And similarly, we have 62 critical endangered, 122 endangered, and 179 vulnerable species. So now we are trying to understand to what extent, and if we could actually use urban areas for plant conservation more in general, to trying to reframe the narrative that urban areas are bad and they are evil in terms of, plant invasions, for example. So we can actually think how to use people gardens, for example, for a positive outcome, which is to preserve biological diversity overall. And finally, just some thoughts about urban invasion science. As I said, we didn't necessarily delve into this data set yet. You're more than welcome to use the data yourself and play around with it. So far we found that about 372 species, so 8% of GUTI, are listed in the Global Register of Introduced and Invasive Species, so GRIS. So this means that some of these species might have potential for biological invasion, at least in one country. And it's a pretty significant number if you consider that these species are only trees and some shrubs. So we are not accounting for any of the other life forms overall. So we cover a significant number of genera and families. So it means that potentially biological invasions could be behind the corner if we were to introduce some of these species and cultivate them in the wrong place. Really, the bulk of these species are essentially 21 species that have been recorded to have potential invasion in 10 or more countries. And among these species, 8 are actually, that are listed here, are actually propagated and planted in more than 50 urban areas globally. So these are pretty common species that they are very well known to be problematic somewhere. So now the question is to what extent we can limit some of these species and their reproduction. Some of these species are listed as weeds, and essentially, depending on which level of government in which country, but some are already excluded from potentially being propagated. In Australia, we have pretty strict biosecurity rules, so we are safe, but in other countries, legislation might be much more lax. So it's our hope that just putting essentially information out there, urban managers might be able to do the right decisions in terms of avoiding planting and propagating material that might be problematic down the future. So where we are going now, well, many different directions. We hope to essentially update regularly GUTI. There are many countries where essentially the inclusion and the collection of tree inventory data is becoming the status quo. For example, in Italy, just because I'm Italian, we just passed a legislation whereby for every town of above 1,500 people, they will need to collect tree inventory data by law. So it's becoming a requirement. And there are many cities worldwide doing this. So it's our hope that in the future we might have several versions of GUTI with better and better data. Better data means that we can actually add some phylogenetic details at some point for some of the, at least the species for which we have phylogenetic data for. But ideally also other traits that are related to the trees. For example, the morphometrics, just simply allometric data tree height, canopy dimensions, and all of that, that would be great to be added as at least in a subset of these cities. It entails a lot of work to clean and homogenize data that is being collected in so many different ways. Some of these data might be categorical, some of the data might be continuous, so it's really challenging to do so. And other things relate to information on horticultural and trade information. In Australia, we have access to live availability, market availability of different species. So we have a very high definition data of which plant is where and the volumes of these different offerings across the countries in different regions, whereas in other countries there is completely no certainty about it. And we would like to set a global standard for data collection and homogenization and cleaning, because it's been quite a messy and quite a time-consuming process so far. We would like to include also information about cultigens, varieties, cultivars, and so on. So that's something that trying to understand how to best approach, because it's challenging in terms of even assigning some of these varieties and cultivars and cultigens to one species or two parents and so on. So not easy task, considering that some of these cultigens and varieties are also owned by the producers, so they are trade marketed, and we don't know necessarily where they're coming from and to what extent they diverge in terms of like ecological characteristics and traits from the parents. So that's something that we should really look like. And in Sydney, we are currently profiling our entire forest. We have 652 species that are planted across Sydney. So it's a very diverse urban forest, but we're using essentially DNA techniques to be able to profile the entire forest, to try to understand to what extent these different trees coming from planted in different parts of Sydney are the same thing, or they are coming from completely different distributions and so on. I'm just gonna stop here, and if you have any questions, just let me know or just drop me an email.